In today's video, we're going to talk about covalent bonding and polyatomic ions. We're going to talk about the definition for covalent bonding, and we're going to go through the electron configuration diagrams of some very common covalent compounds. We're then going to talk about average bond enthalpy and how that's affected by single, double, and triple bonds. And then lastly, we're going to talk about some polyatomic ions, which have both covalent and ionic character. So covalent bonding is only non-metallic elements. So let's just remind you of where they are. So if we look here, periodic table, and we see our stepped line coming down over here. We can see on the right that there is the non-metals, okay, on the left is the metals, okay, but only the non-metals bonding will give you covalent compounds. Okay, so, and that works for your four A levels apart from the very odd exception, okay, so it will generally work for everything that we should do. Now, the definition required is the electrostatic attraction between a shared pair of electrons and positive nuclei. So it's required, so make sure that you remember it and put it on your list to revise for your exam. Now, common examples of covalent bonding start off with the most simple, which is hydrogen. So hydrogen has one electron, and if you put the two hydrogens up, because we're putting the two hydrogens that are here, okay, you can start to be able to draw covalent bonding. So first of all, it's about a shared pair of electrons. Okay, so we have a rule that generally works, and the rule is all the unpaired share. So if you see an unpaired electron, they're going to share. Now the question is, where are they going to share? Okay, well, they're going to share between two atoms. So what we can do is we can draw the two shells, and there's your two shells drawn. Notice I've overlapped them, and in the center here is this shared area. Okay, so that's your shared area. Now, then all I do is I take the electrons. So we have our orange cross here. Okay, and we'll take that, put it in there, and we put it in the shared area. So if it's on its own, we put it in the shared area. Okay, so if that is on its own, we now have H. Okay, and that's something you're used to at GCSE level. Now we move on a little bit in A levels. What you can do in A levels is you don't actually have to draw these shells. Okay, they don't need you to draw the shells. Okay, so you can actually just draw it like this. Okay, there's our two H's, and all I do is take the electrons and put them in the center of the two H's. And that's also acceptable. Okay. Now, one pair of electrons equals a single bond, so you can also draw this as H bonded to H, because that's a single bond, a pair of electrons is a single bond, and if you're drawing electron configurations, both these are acceptable. But this is why when we draw organic compounds, we draw a single line, because we know that where there is a single bond, there is a pair of electrons. Now, let's do a slightly more complicated example, which is HF. So in HF, you've got one electron in the hydrogen, and then you've got your 7 electrons in the F. We do the same thing, okay, and we can put them in our shared area. But this time I'm going to jump straight to without the shells, because it's just a little bit simpler. So if I go, there's my H, and there is my F. So I've got my H and my F, and first of all, I'm going to pick out my unpaired. You see that's unpaired there, there's an unpaired electron there, unpaired electron there. Okay, so I'm going to share both of those. So I have to put those in between the H and the F. So there's one of my electrons, and there is the other one of my electrons. Notice I'm doing a dot and cross to show the different elements, okay, or in this case, different atoms. Okay, and then all I have to do is once I've drawn the shared pair of electrons, I just draw in the other electrons. So I just place those around as if the shell was there, but I just don't draw the shell. And that diagram is totally acceptable. Okay, you can draw the shells if you want, you can just overlap them, make your shared area, put the electrons in the center, or you can just draw it like this. Now again, there's only one pair of electrons there, so if I'm drawing the actual bonds, okay, it's a single bond again. Okay, so there's your two simple examples to start off on covalent bonding. So let's go on about some slightly more complicated versions. So we have CH4, and let's draw out our elements again. You can see there's 4 hydrogens, so I've drawn 4 hydrogens around the outside. We've drawn our electrons. If we draw our electrons properly, it's really important that you can draw them properly, and that means that you will have 4 electrons on their own. So the way to draw them, remember, is put 1 electron there, then here, and then pair them up. So if you do that, you will have 4 unpaired electrons, and you'll have another 4 unpaired electrons around the outside. So it makes sense that all the electrons here share. So what we can do is we can jump into doing it without the shells again, and we can go, there's our H, there's our C, and there's our H. Okay, so then we look at it and we go, right, where are our hydrogens? Okay, we're going to share all of them. Well, it makes sense, therefore, that we put our hydrogens in. Remember, they have to be between the elements. You don't have to draw the shells, but they have to be between the elements. And then I'm going to draw my carbon ones. Okay, and there you have a diagram of methane. And again, 1 pair of electrons equals a single bond. So I can draw that again, just as single bonds. And that's where your drawing of methane normally comes from. These single bonds, each one of those is a pair of electrons. Now, if we try another one, this time I'm going to try ammonia, very common one. Okay, we're not going to draw the shells this time, we're going to see if we can do it straight from. So a way to do it straight from it is to look at how many hydrogens there are and look at this element at the start, and usually that surrounds the element in the examples you're going to do anyway. Okay, so if that is the case, we put our hydrogens there. There's our hydrogens. Okay, and then from there, we can then look at it and go, right, how many electrons does nitrogen have? If you've got a periodic table in front of you, you know it's in group 5, and therefore it has 5 electrons. Okay, so I'm going to draw the 5 electrons. So there's 1, 2, 3, 4, 5. Okay, so I've done 5 electrons. There's my 5 electrons drawn. And then all the unpaired share. So it makes sense that all of the electrons on the hydrogens which are unpaired will pair up with the ones that are unpaired here. Okay, there's my picture of ammonia. And again, because a pair of electrons is a single bond, that's why you're used to seeing ammonia as this. Okay, so there you've got 2 more slightly complicated examples, and without the shells, if you don't want to draw the shells, and showing you the bond. Our next example is H2O. And we're going to show you another version that's very similar to H2O very soon as well. So we'll jump in straight away and look at our electrons, and we can see, again, very similar to before. Okay, and we're going to jump straight into, okay, we've got H. There you go. So this is my H2O. And I'm just going to say, again, unpaired electrons. There's my unpaired electrons. Again, it really depends on, you must draw these electrons properly for this to work. Okay, and then I just put my electrons in. Okay, there's my electrons. And my unpaired. And go in. Okay, and again, if I just drew my bonds, okay, and there you go. Right, so that's my common drawing of water, and you can see it's a process that if you keep on doing it, practice it a few times, it's quite straightforward. So I'm going to show you another one that looks very complicated to start with, and if you're watching the video, it might be a good idea to pause it, try and draw it yourself, and you'll see something very similar coming out. So here you have your fluorines. Deliberately draw them like this. If you draw them again properly, you will get that unpaired electron here, unpaired electrons here, and unpaired electrons there. Okay, so if I then do what I have done before, because I've got OF2, so I've got the F, I've got the O, and I've got the F. Okay, and then I start drawing I'm just going to draw my unpaired electrons to start off with. Okay, there's my 2 unpaired, so I know that's going to share. Okay, and then I've got my 2 unpaired here, so there's 1, there's 2. And then all I have to do after I've drawn that is draw in all the other electrons that were already there. Okay, so there you go, and then drawing all my fluorides. Okay, there's my fluorides, my fluorine, sorry, electrons. So here's my fluorine electrons and my oxygen electrons there. So if you look at this, if you can take that section right there, and then look at this section, and then look at that section, you notice they're exactly the same. So that, and also single pair of electrons between each, and therefore that is OF2. And that's a common example I've seen in a lot of exam papers. Okay, but you see it's very similar to water. Okay, and it looks very similar in terms of the bonding, in terms of the electrons. We're now going to go on to discuss multiple bonds and then talk about average bond enthalpy. Now, first of all, double bonds. The most common one we're going to come across with is oxygen. So let's look at oxygen. Oxygen is O2. Okay, so that means we will have 2 oxygens like that. Okay, and if we draw one of the oxygens as crosses and one of them as dots, we know from previous diagrams that we have two unpaired electrons in each oxygen. So I'm going to put the 2 unpaired there. Okay, and then I'm going to put the other 2 unpaired there. Really important, if you draw them without the shells, you put them in the middle of the 2 elements. And then all I do is draw in all the other electrons. So if you remember from the previous diagram, there was 2 pairs. Okay, and there's your 2 pairs as well. So remember, oxygen is in group 6, so 6 electrons, 1, 2, 3, 4, 5, 6, and the same on the other side. Now, the important thing here is that now you have 2 pairs of electrons, okay, which means that if you're drawing it just as bonds, that is why oxygen looks like that. Okay. Now, if we go on to a triple bond, the most common is nitrogen. There are others, but the most common is nitrogen. So if I then put my nitrogen, which is N2, okay, there's my Ns. And then if you remember from my previous diagram, I had 5 electrons in the outer shell, and there was 3 of those electrons were unpaired, okay, in nitrogen. So 3 are unpaired, so I'm going to go 1, 2, and 3. And then I'm going to draw the other ones. Remember, the unpaired share. Okay, so if we then just draw the other electrons, so there were 5 electrons in total, so 1, 2, 3, 4, 5, okay, and then we draw the other electrons here as well. Okay, then we look at that and we go, right, okay, we have done 3 pairs of electrons, and therefore that is why we draw, and that's why you see nitrogen as that. Okay, so that is your nitrogen triple bond and your oxygen double bond. Now, what's really important is average bond enthalpy. So average bond enthalpy basically is the amount of energy it takes to break 1 mole of bonds in the gaseous state. So basically it's an indication of the strength of the bond. So all we're saying is a single bond, imagine if you're holding on to something with 1 hand, it's not as strong as you hold on to it with 2 hands. Or if by some miracle you had 3 hands, it wouldn't be as strong as if you held on with 3 hands. Okay, so it makes sense therefore that the bond enthalpy, the amount of energy taken to break the bonds, okay, is greater for double and then greater for triple. So you need to remember it's going up as you go towards the triple. And we'll discuss that again in another video. We're now going to go on to talk about polyatomic or molecular ions. They have a bit of covalent and ionic character, so therefore are a little bit more complicated and are more common in the exams. So it's a good section for you to make sure you can do. The most common one is hydroxide. Okay, and if we look at hydroxide, and we do it as we've been doing in the last few slides, we just draw out our elements. Okay, if we remember that hydrogen had one electron that was unpaired, so that will definitely share. Okay, and we remember that oxygen had two unpaired electrons, so one of those unpaired electrons is going to go there, and then we're going to draw out all our other electrons as they were in the original diagram. Okay, so there's our 6 oxygen electrons. Now, at the moment, what the really important thing is here is to remember that this is neutral. Okay, so this is totally neutral. I have not added any electrons. I have not taken away any electrons. This thing is completely neutral, just like everything else that we've done so far. If you add electrons, you're going to get negative. If you take away electrons, you're going to get positive. Okay, so that means if I then look at this and I follow my rule, I've got a minus here. Because I've got a minus, that means an electron must have been added to make it negative. Now, the important thing is here is that you use the electron or make the electron a different shape or a different, so for example here you've got crosses, you've got dots, you have to use a different shape. The shape that you use can be variable, okay, but the most common ones we use are triangles. For example, stars are on marked schemes and things like that. So I'm going to use triangle. Now, if you put this into perspective, this is normally sodium hydroxide, okay? So it comes from sodium hydroxide. So that electron is going to come from a sodium, okay? And therefore, that means you can tell the crosses are the oxygen, the dots are the hydrogen, and the triangle is from that metal ion, which normally is sodium because we use sodium so much. Okay, now let's go for a common one which has been seen on exam papers before, which is carbonate. Okay, now carbonate, a bit more complicated, and therefore in past exams they've actually given you the structure. So here is the structure right here. So I'm going to show you how to take it from the structure to this kind of diagram. Okay, so if that is the case, all you do is draw the elements out like you've done before. So I will put the C, okay, and then I'm going to put the O up in the corner, the other O down here, and then the other O. Now you've got a similar diagram to what you've got here. You then look at your bonds. So if you look at your bonds, you can see the single bond. Now if we remember, the single bond is a pair of electrons. Okay, so a pair of electrons. So in this case, we're going to do our oxygens as crosses, okay, just like we did above. Okay, so I know that that's a pair of electrons and one of them is from the oxygen. I know there's another single bond coming down here. Okay, and I know there's a double bond here. That must mean there is two pairs of electrons, therefore 2 electrons must have come from the carbon. Now if you look at that, that means there's 1, 2, 3, 4 electrons from the carbon, which is how many electrons we actually need anyway. Okay, but I'm just copying this diagram. And we can then see, if we do the oxygens as dots this time, okay, and we can say, right, okay, oxygen normally has 2 unpaired electrons. That is a double bond, okay, so therefore the 2 unpaired would go there. This is a single bond, therefore I must have had one of the electrons from the oxygen, and that's a single bond again, so one of the electrons from the oxygen. So I'm not drawing it with shells, and I'm just showing, look, there's your single bonds, and this is your double bond here. You then have to draw all the electrons in that would normally be there. So I've drawn my carbon electrons because these are the orange ones, as you can see here. The red ones and the dots are the oxygen, so I know there's 6 electrons that are in the oxygen, so let's just draw those 6 electrons out. And there you go. There's my 6 electrons, 1, 2, 3, 4, 5, 6. And then I copy my 6 electrons out again. Okay, and then I do the same here. Now remember, this time though, there are 2 electrons from the oxygen already there. So I need to put 6 out, but I've already got 2. So therefore, I don't need to put 5 out, I need to put 4. So there you go. 1, 2, 3, 4, 5, 6. And again, 6 electrons from the oxygen there, 6 electrons from the oxygen there. Now I want to emphasize again, this is currently neutral. Okay, so this is currently neutral. Now, on here you can see that this is 2 minus. So this is 2 minus. That means it must have gained 2 electrons. Where does it gain 2 electrons? Well, it gains the 2 electrons to make that full outer shell. Just like, again, we made that full outer shell. Just like we've been making the full outer shells all the way through when we're doing these diagrams, okay? So that electron must have come from somewhere else. Okay, and then this electron must have come from somewhere else. So all the way through our diagrams, we've been making all the unpaired share. At the same time, we can do another check on top of that to make sure there's a full outer shell. So we can see here, full outer shell, 8 electrons. We can get 8 electrons here, so you've got 1, 2, 3, 4, 5, 6, 7, 8. So a good check is to make sure that is full. And you can see again, look, the rules. If there's a minus, you must have added 2 electrons. These are our blue electrons down the bottom. And we added those to get that full outer shell. And here we added this one to get our full outer shell. Again, 8 electrons. Okay, let's try another couple of examples. So the 2 more difficult examples we're going to do are sulfate and phosphate. So sulfate, as you can see here, is SO4 2 minus. And normally in the exam, you would be given the actual picture of the ion itself and shown all the bonding, just like you were in the previous one. So what we do is we look at it and we go, right, okay, let's draw out our atom just like it's drawn out there. So there's your S, and there's your O, there's your O. Right. The important thing before you start is to look at the diagram and look at this and try and match across like we did in the last one. So let's do the sulfur electrons. We know that's 6 electrons in total, but let's just follow the bonds really first. So if you look here, there are 2 bonds, which means that it must be 2 pairs, which means I must have had 1 electron from for one pair and then 1 electron from another from the sulfur. Remember, we need 2 pairs, so we need to have the electrons donated from both. 4 electrons in total, so we need 2 from the sulfur. We do exactly the same because there's a double bond on this side. Okay, there's a single bond down here, so only 1 of the sulfur electrons, and a single bond here, so only 1 of the sulfur electrons. We then go to what is happening with our oxygen electrons. So our oxygen electrons, okay, again, we can count them all out and see this, but it's easier just to follow the bonds. There's a double bond there, therefore I must need 2 electrons to complete my 2 pairs. I must need 2 electrons to complete my 2 pairs. And I must need the 1 electron in each of those to complete my pairs. So done with bonding electrons. The interesting thing here is the fact that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 electrons in sulfur, in the outer shell of sulfur. It doesn't follow the octet rule, so sulfur doesn't follow the octet rule. Okay, but oxygen does, and that will become really important just as we do the remaining oxygen electrons. So let's do the remaining oxygen electrons. We've already counted out 1. We know there are 6 in the outer shell. So let's count them out, and again, it's about putting those electrons on properly. Okay, let's copy that down to that one because that's exactly the same. You can see, again, I've got 6 electrons, 6 electrons. Here I've already got 2 electrons out, so I just need to add 4. And then the top is the same. Okay, so we've got, and that's all our electrons done. Remember, this is neutral at this stage, totally neutral. But I need to have 2 minuses, okay? So I need to add 2 electrons. Now, where do I add those 2 electrons? Add them where I think I can get a full outer shell. Now, here, oxygen should have 8 in its outer shell if it's going to be full, okay? And it only has 7. So that's where my extra electron goes. And that's where my extra electron goes there. Okay, so we now have a picture of sulfate. Now, if we move on to again, a slightly more complicated example and an exception in terms of the outer shell is phosphate. Now phosphate, again, we're going to copy out. Remember, you can stop this video, you can draw it out, you can check your answer, okay? So if we do that and we go, here's my phosphorus, okay, and I'm going to put my oxygen there and then down there. See if you can do it quicker than I'm doing on the board if you feel confident, okay? So we go to the phosphorus and we know, again, let's look at the bonds. So I'm going to do the phosphorus as dots, single bonds there, so it must have donated 1, and I'm looking at the bonds again. And that's just by looking at these bonds on the on here. I've got a double bond here, so I must have donated 2 or shared 2, and then I've got 1 bond here, so I must have shared 1. And then I put my oxygen electrons in, same process. Okay. And there we go. And now I have a double bond there, like I've got there, single bond, single bond, single bond. Then I put the rest of my electrons in. Okay. Okay, and I've put all of my oxygen electrons in. Okay, and I've counted them all out. And then I'm looking again, 3 minus. 3 minus, I have to add 3 electrons. Where do I add it? To fill the outer shell of that oxygen. So there, and then it will go here. Okay, and then it will go here. And there you have a phosphate ion with 3 minuses on it, all the electrons drawn correctly. We're now on to our last type of covalent bonding, which is dative covalent bonding. Dative covalent bonding is just where only one atom donates both electrons to the bond. So it's really important that you focus on the one atom donates both electrons to the bond. And that's normally what's called a lone pair, and we'll talk about that in a second. Now let's look at our 2 most common examples. So our first one is carbon monoxide, and I'm going to take you through how you do this. So first of all, let's look at the carbon number of electrons and the oxygen number of electrons. So if you look at the oxygen number of electrons, I'm going to do the oxygen as dots this time. Okay, and you can see that there is a triple bond there. But if I look at oxygen's electrons, oxygen only has, if I just put the oxygen electrons here, okay, oxygen only has 2 single unpaired electrons. It only has that. So if I'm saying that the 3 bonds here, I know that the 2 unpaired must share. So I'm going to put those in the center. Okay, so they are sharing. I know that that must include 2 electrons from the carbon. Okay? So it gets a little bit complicated. So you know that that is happening. You know because you've got 3 bonds there. Now we have to do the 3rd bond. The only way in which the 3rd bond can happen is if a pair of electrons is donated from one of the atoms to create that 3rd pair. So what happens is the oxygen will donate one of its pairs. Now, these pairs are called lone pairs because they're not normally involved in bonding. So when you get a dative covalent bond, it's because a lone pair is donated, and that's a pair of electrons. Okay, so that pair of electrons is donated into the center. So there's the pair of electrons, and they're donated into the center, which leaves a pair of electrons here. So we go 1, 2, 3, 4, 5, 6. Okay, and then that also leaves 2 of the electrons in the carbon. Now, you would normally expect those electrons to share because they're unpaired on the carbon. Okay, but this is a peculiar example of bonding which you need to get used to. And you'll only go through so many examples in this course. So carbon monoxide is one that you need to learn. Now we can draw this, again, in a slightly different way. So if we have, there is our 2 bonds, and we want to draw a 3rd bond. Well, sometimes the 3rd bond can be drawn like an arrow. And it's drawn like an arrow to indicate to you that it's the oxygen's electrons that are donating to form that dative covalent bond. So that 3rd bond, which is this pair right here, okay, is our dative covalent bond. So I would recommend that if you are learning any examples, you definitely learn carbon monoxide. My favourite example, though, because I think it is a bit clearer, is the ammonium ion. Ammonium ion is made by taking nitrogen and a H+. Okay, so if I draw the nitrogen here, okay, and I say, okay, here is your hydrogens going around the outside. Okay, and you draw normal ammonia. And I'm going to draw the nitrogen this time as dots. And this is just our ammonia diagram that we've done earlier in the film. Okay, there we go. And there you have ammonia. Now, if I'm going to react H+, okay, so H+ has no electrons. It's lost one of its electrons. Okay, it is just H+ on its own. So therefore, what happens is these electrons from the nitrogen donate themselves towards that H+. Okay. Now, that means you get a dative covalent bond because the lone pair comes from one atom, is donated up towards the H+. Remember, this was H+. Now that means overall, this will be positive, okay? So that overall, this will be positive. Now I'm going to go through quickly why, for example, that would be positive, okay? And this is often missed by students. So if I count the number of electrons, count the number of electrons here is 8. Don't forget the 2 in the center. So there are 10 electrons. Okay, if you look at the protons, there are 7 protons in the nitrogen, which means 10 protons there, and got 11 protons because we've got 4 hydrogens, so 11 protons. So in this whole thing, we have one more proton, and then we have electron. Therefore, the whole thing is plus. Now, remember, this was made by ammonia reacting with H+. H+ has no electrons, so therefore, that's why the electrons donated towards it. Okay, and you can see this is a bit of a mixture of that diagram over there, showing you that the lone pair of electrons donate. This is your dative covalent bond, okay, and where only one atom donates both electrons to that bond. And it's really important that you're familiar with how to do dative covalent bonding.